This video explores an introduction to functions of several variables. So we'll start out reminding ourselves about functions of a single variable. Those are where we have one input, a single input, one single dependent variable, and independent variable, one single independent variable, and it produces one output, one dependent variable. So some examples, I'll just give you a few. These are the ones we've been working with so far in the semester. So f of x equals something like x squared plus 3x minus 7. G of x is 61.6 e to the 0.713t, or h of x equals 7x plus 2 over x squared plus 9, right? Those are the types of functions we've been dealing with up until this point, functions of a single variable. One input, one output. So what does it mean to be a function of more than one variable? Well, that means we have more than one input, more than one independent variable, and we have still one output. So what do those sort of functions look like? And some of them will kind of sort of look similar to what we've had before. So something like f of x and y is equal to x squared plus 4xy plus y squared. You might also see this as z equals x squared plus 4xy plus y squared. Okay. Another example might be if our population or profit or something like that depends on two variables, both x variable and a time variable. You might see something like 61.6 e to the 0.713t plus x times t. Or there are functions, that's just a functions of two variables. You could have functions of three variables, or 4, or 5. So here's an example of three variables. G of x, y, and lambda, that's the Greek lowercase letter lambda, is equal to lambda over the ln of x plus y. So notice three inputs, but you still get out just a single number, a single output, if you plug in variables for each of the input variables. So let's do that. Let's evaluate functions of several variables just to make sure we know how that works. So here we have a couple of functions. The first one is f of xy equals x squared plus 4xy plus y squared. And we want to find the value of this function when x is 0 and y is 1. So notice that 0 is our x variable and 1 is in the y variable position. So that means wherever we see an x, we're going to replace it with a 0, and wherever we see a y, we're going to replace it with a 1. So that looks like 0 squared plus 4 times 0 times 1 plus 1 squared. And that's 0 plus 1 is 1. The next one is we would like to know what this value of f is when x is negative 2 and y is positive 3. Again, wherever we see an x, we're going to replace it with a negative 2. So it starts out with x squared, so that's negative 2 squared, and then plus 4 times x, which is negative 2, times y, which is 3, and then plus y squared. That's 3 squared, so this is 4. Let's see, negative 8 times 3 is minus 24, plus 9 is negative 11. So in this function, we had two inputs. The first time it was 0 and 1, and we got out the output of 1, and the next time the input was negative 2 and 3, we got an output of negative 11. This next function is a function of three variables, x, y, and lambda, and we're going to evaluate the function lambda times ln of x plus y when lambda is 1, x is 1, y is 5, and lambda is 10. So we want to make sure that we're evaluating this. This is x, this is y, and this is lambda. All right, so this says lambda ln of x. So which is the lambda number? 10 times ln of x is 1 plus the value of y, which is 5. The ln of 1 is 0, so this is 10 times 0 plus 5, which that result is 5. Similarly, if we want to know what g of e and negative 4 and square root 2 is, x is the first position, e, y is in the second position, that's negative 4, and lambda is in the third position, square root 2. So again, the original function is lambda times ln of x, so lambda is square root 2, ln of x, x is e, plus my value for y, which is negative 4. ln of e is 1, so we get square root of 2 times 1 minus 4, and so this result is square root negative 2 minus 4. Okay, so we just have to make sure we put the right numbers into the right variables. That's really the tricky part of that. Now when we are graphing functions of two variables in particular, we have two inputs and one output. So if we want to compare this to what graphs of functions of one variable look like, well, functions of one variable, we had one input and one output. And when we graphed them, our horizontal axis was our input variable, which was oftentimes x, and then the vertical axis was our output variable, which was often y. So we could draw the relationship like y equals x squared. The input variable is x, so when x is 1, 1 squared is 1, so you get the point 1 comma 1. When x is 2, 2 squared is 4, you get the point 2 comma 4, etc. So how does it work when you have, for example, a function of two variables? Well, it turns out the input variable then is an entire plane, right? It's not just represented on an axis, it's represented by the xy plane. Okay, so if you kind of imagine the floor in your room is sort of that xy plane, and then the corner is sort of the z-axis. It goes up, so it's in 3 dimensions. Graphs of functions and two variables are surfaces. It's a 3-dimensional graph, not just a 2-dimensional graph. And so when we put something like, when we have a function, let's say f of xy equals x minus 2y, and we want to plot the result of 0, f of 0 and 1, well, that's 0 minus 2 times 1 is negative 2. This really means we're plotting the point 0 comma 1 in the xy plane and then going down 2 units on the z-axis. So if we were to try to graph that, that's 0 comma, and here's 1, and then if you imagine the z-axis going down, 1, 2, so it might be somewhere right around there, 0, 1 comma, negative 2. On the other hand, if I wanted to figure out what f of 3 comma 1 is, that would be 3 minus 2 times 1, which is 1. So then I'm plotting 1, 2, 3, comma 1, and then up 1. So I get the point 3, 1, 1. So 3 and 1. So I figure out where that is, and then go up 1 unit on the z-axis. So 3 comma 1 would be 3, 1, 1 above the x-axis. So if the output z is positive, the point xyz is going to be plotted above the xy plane, kind of like, you know, above the floor. And if the output z is negative, then the point is plotted below the floor. And we can actually plot a couple of different functions of two variables when we get these surfaces, and we can take a look at what they look like. In the handout, you have, I have a link in there to a website that has a program called GeoGebra and 3D graphing. And there is a GeoGebra, if you have an iPad or something like that, there's also an app you can download for the iPad. So I'm just going to go through just a couple and just to see how cool these look. So this first one is the function z equals x squared plus y squared. And so you can see it kind of has this parabolic shape, kind of like a bowl or a cone sort of shape. And it's basically, if you take it in cross sections, if you sort of cut it this way, they would look like circles, right? You can see kind of at the top, there's this sort of circular shape. And so if you kind of look down on it, it looks like, you know, circles. The next one is the square root of 1 minus x squared minus y squared, and you'll notice it looks like a hemisphere, half of a sphere. And in fact, that's true. You get the top half because we can only take square roots of positive numbers. So if you're only taking the square root of a positive, the output is only going to be positive. So you notice the hemisphere lies completely above this xy plane here, right? Here's the xy plane. And so the hemisphere lies above. It sort of sits on the floor of the xy plane. This next one is kind of cool. This is 1 over y plus x squared, and it actually comes in a couple parts because you kind of have this area where y plus x squared is equal to 0, right? You can't divide by 0, so wherever that happens, there's a break in the graph. So you can see there's this empty space up in the top here, right? There's this empty space here, and there's empty space between the two parts here. So you get these sort of two pieces of this function. Kind of like when you had vertical asymptotes. It's kind of sort of that same sort of idea, except that it's not just a single line you can't cross. It's like a whole chasm, a whole part of the 3D area you can't cross, right? You get these gaps, these large gaps. There's another one, x squared plus y squared plus 1 over x squared plus y squared. Those of you who bake or have helped someone bake a bundt cake, this kind of looks like a bundt pan. Now remember, this is sort of cut off, right? This would continue going on here, and it would eventually, right, you're kind of seeing this surface goes up and up and up and narrows and narrows and narrows, whereas on the outside it's continuing to go out and out and out and out. So it's kind of a bundt pan where the sides keep growing out and then the inside gets narrower and narrower. Well, that inside is getting narrower and narrower because of that denominator there, x squared plus y squared. And we'll talk about that in just a second. Okay, so we want to find the domain of a function of two variables because we're going to be examining these functions. We're going to find maxes and mins of them, just like we did for functions of single variables. And so how is this similar to finding the domain of single variable functions? And it's actually, a lot of it is very, very similar. We're really still trying to avoid these three things, right? Can't divide by 0. We can't take square roots of negatives. And you can't take the log of 0 or negatives. Okay, and so those three rules are the same three rules we're going to abide by in finding the domain of functions of two variables. Okay, so let's take a look at a few examples. So finding the domain of a function of two variables, if our function is f of xy equals x squared plus y squared plus 7xy, this should look to you a lot like the polynomials we examined, like f of x squared plus 3x plus 7, right? The variables are raised to whole number exponents. It's not a quotient. It's not a rational function. There's no square roots or anything. And so the same rule applies here. We're not dividing by 0. We're not taking the square root of a negative. We're not taking, there's no logarithms involved. So the domain is all reals. Or, sorry, the domain is not all reals. The domain is the entire xy plane. Okay, we can plug in any x value you want. You can pick any point in the xy plane, any pair x and y, and plug it in, and you'll get an output. And so the way that we're going to write this is domain is equal to the set of all points, x, y, set of all inputs, such that x is any number between minus infinity to infinity, and y is any number between negative infinity to infinity. Okay? The next one does involve a square root, right? So when we have square roots, we must have 1 minus x squared. Sorry, that should be a minus. Little error there. Oops. I need to erase that. No, it won't let me erase. Oh, here we go. That should be 1 minus x squared minus y squared. And that must be greater than 0. Or if you prefer, 0 must be less than 1 minus x squared minus y squared. Doesn't really matter which way you choose. In any case, if we take a look at this one here, what we can do is add x squared and y squared to the other side of the inequality, or to both sides, and then that gives you this inequality. But like I said, you can write this, think of this backwards and forwards. This is the same as x squared plus y squared must be less than 1. And so that's the condition that we have here, right? That whatever x and y squared are, if you add them together, they have to be less than 1. And if we kind of think of this as in a slightly different way, right, if we sort of factor out a negative from the x squared and y squared, it looks like that. So you can clearly see, in order for this to be positive, x squared plus y squared has to be less than 1. And so we're going to write that as the domain is equal to the set of all points x, y, such that x squared plus y squared is less than 1. That's it. That's the only condition. So you pick any point in the xy plane that meets that condition. Remember, this was the hemisphere, right? This was the green hemisphere that sat on top of the xy plane. And if you looked down on it, you could pick, it would look like a circle, right? If you looked at it from the top, it would look like a circle. And in fact, it would be the circle x squared plus y squared equals 1. So anything less than or equal to 1 would work. And in fact, that means I have to make a correction here. You can't take the square root of 0. So let's go back and make this less than or equal to, right? Because those are all less than or equal to. Right? We can actually get out 0. We can take the square root of 0. So we can make this x squared plus y squared less than or equal to 1. All right, a few more here. Next one is x squared plus y squared plus 1 over x squared plus y squared. And here we have to worry about dividing by 0, right? This part here cannot be 0. And in fact, the only way that that's going to happen, since if we square something, it becomes positive, right? Squaring x, positive, plus squaring y, positive, should result in a positive number, with the only exception they can't equal 0. So we can plug any other pair of numbers we want in here. So the way that we write that is D is equal to the set of all ordered pairs x, y, such that that point cannot be point 0, 0. All right, the very last one is a little tricky because we have a problem of not only division, but also a natural logarithm. So let's first take care of the natural log part. So we can't take the natural log of a negative or 0. So that part here must be strictly greater than 0, right? You can't take the log of a negative and you can't take the log of 0. So that means if we add x to both sides, that y must be greater than x. The other condition we have is it must be ln of y minus x cannot be 0. Well, if we remember the relationship between the natural log and the exponential, this means that y minus x cannot be equal to 1. Right? Because you can't take if you take the logarithm of 1, you get out 0. So we can't have y minus x equaling 1. So this means that y cannot be equal to x plus 1. So not only do we have to have that y is greater than x, but you also have that y cannot be equal to x plus 1. So that's how we'll write our domain. The domain is the set of all points x comma y such that y is greater than x and y cannot be equal to x plus 1. That's one way to do that. Okay. And that's probably the most complicated one that we're going to see. And I think there would be a way to combine that into a single one, but we're not going to worry about that for right now. Okay. That's pretty much it. All right. Thanks for watching.